Welcome to our Chapter 12 lecture video. Today we're going to cover intermolecular forces of liquids and solids. So we don't really talk about intermolecular forces when it comes to gases because gases have so much internal energy that they're able to overcome the intermolecular forces and essentially have no interaction between particles. Today's focus is going to be these forces and the heat and energy calculations regarding physical changes. So when we melt or evaporate, when we go from one state to another state, this involves either an absorption or a release of energy. So when we go from a lower energy phase of matter, solid is our lowest energy. It has the least amount of internal energy relative to the intermolecular forces. A liquid has intermediate in energy compared to its intermolecular forces. Gases have essentially no intermolecular forces compared to their internal energy. So as we go between these states, we either have to absorb or release energy. We can think of this as exothermic or endothermic processes. These will be the only calculations for this part of the chapter. Everything else is going to be conceptual. It's a very conceptual chapter. Intermolecular forces are the reason for all the things that we experience in this world. So we might be able to interact with what we call the macro scale world, but the micro scale and the atomic scale world is where all of these properties build up to create what we're actually able to observe. So we can look at a molecule of water or a bead of water, not a molecule of water, a bead of water and see that it coalesces into a sphere. We would, say the cohesive forces or the adhesive forces, I forget which are which, not important for chemistry, are the response or responsible for this, globulation of the water. We can relate that to the attractive or intermolecular forces that exist because of the difference in polarity between hydrogen and oxygen and a whole bunch of other things that we're going to talk about in this lecture. So, like we said, intermolecular forces are what attract things between each other. These are between different molecules. Interactions between the same molecule, so one molecule of water, how it interacts with itself, is called an intramolecular force. We're only going to be concerned with intermolecular forces. Inter is between two things, intra is between one thing. So we're going to talk about the interactions between two different particles or two different molecules. Very important for how all large scale things work is because things build up from, the base up. The small things really do matter, and they are what result in the ultimate properties or observations that we make. So we talked about this in the previous chapter. We're just going to kind of review. Thermal energy is just associated with the internal energy, which is related to how fast something is moving. We can say that everything has some sort of random motion. The higher the temperature, the more random motion that occurs. Depending on how much intermolecular forces there are, compared to the internal energy, we get different states of matter. So the less intermolecular forces we have, the more likely we're going to be a higher energy state. So remember we said solids are the lowest relative energy state, liquids are in between, and gases are the highest relative energy state. This is in comparison to the intermolecular forces, not absolute energy. So sodium chloride is a solid until like 900 degrees Celsius. That's because it has very, very strong intermolecular forces. Whereas carbon dioxide doesn't really have many intermolecular forces and is not a solid until you get to extremely, extremely low temperatures. At all regular temperatures on Earth, CO2 is a gas. It never takes a liquid or a solid state because it just doesn't have enough intermolecular forces relative to its internal energy. So, more stuff that I kind of just stated, just more slides to spell it out in words. If we want to look at these in more of a depiction, liquids have enough energy that they can pass by each other, but they're still connected to each other. They're still interacting. Whereas gases have so much energy that they're just bouncing off each other. There's plenty of space in between them. They essentially don't interact. Solids are so tightly interacting that they're stuck in place. They have the crystal lattice because there is not enough energy to overcome the force of that lattice. Liquids have enough energy to overcome the crystal lattice. Gases have enough energy to overcome all of the intermolecular forces. So these are just some of the properties from gases. We talked about this last chapter. We don't really care about it for this chapter. Essentially, they have no intermolecular forces, so when we're talking about intermolecular forces, we can't really be too concerned with them. Liquids have intermediate intermolecular forces, whereas solids have high intermolecular forces. Relative to gases, liquids and solids are going to have really high densities, but similar to a gas, liquids have indefinite shape. They'll form to their container, but they have a definite volume. You can't compress them. You can compress a gas, you can't compress anything else. So water has a good amount of intermolecular forces, but not so much that it's a solid at room temperature. It's a liquid at room temperature. Something like sodium chloride or, sugar is going to have so many intermolecular forces that it's going to be a solid. One thing that we'll notice is that larger molecules tend to have more intermolecular forces because there's just more things there to interact with. So we talked about solids, in previous chapters. We have crystalline, which have a crystal lattice that's ordered over some long, array pattern. Amorphous is disordered. There is no order in the long range. So we kind of already said this, but liquids, they'll form to their container because they don't have a definite shape. They can pass each other to whatever's convenient given the situation. Solids are fixed in place because they don't have enough energy to move past each other. They're stuck in some sort of lattice, whether that's a crystal lattice or just an amorphous conglomerate of particles. They're still fixed in place. They're still stuck and locked in a place where all they can do is vibrate. They can't move past each other. So we can use, intermolecular forces to represent surface tension, viscosity, cohesive and adhesive forces. All of our physical properties can be related to intermolecular forces. We're not going to focus on the physical properties, but we can explain them with the focus of this lecture, which is intermolecular forces. So the reason some things can float on water, like, lures or other bugs that, water striders, things like that take advantage of the surface tension, is because the force they apply is less than the interaction between molecules. So these molecules are going to interact with some amount of strength depending on their intermolecular forces. If the force applied to the surface is less than that interaction, then the surface won't be broken. So all of these things that can, sit on the surface of water have extremely large volumes to their mass. And so that gives them a lower force than what is required to break this interaction. If you just plunge your hand through water, it goes, right across. But if you lay a leaf or something incredibly light compared to its volume, the amount of area that it displaces, then it can float on top of these interactions, so to speak. Viscosity can be explained by things having more intermolecular forces. We can think of this as, friction between molecules. If molecules are holding on to each other a little bit longer or tighter, then you're going to have an increase in viscosity, and those things are going to flow more slowly. They're going to behave a little bit more like a solid, where they kind of get locked in place, but, not truly locked in place. Maple syrup is a great example of this. Maple syrup is a very large molecule with a lot of different types of bonds in it that can all interact with each other. That's why, at low temperatures, if you take it right out of the fridge, it doesn't really want to pour very well. That's because, it has a very high melting point or freezing point. Evaporation is just a, physical property. We can determine what the vapor pressure is by the chemical, formula, looking at what type of bonds are in it. We can then say, this has more or less intermolecular forces based off the arguments that we're going to make and bring up later. But in general, we can increase the rate of evaporation by increasing the temperature. So if you increase the energy, more particles are able to escape the intermolecular forces into the gas phase. You can also decrease the strength of the intermolecular forces. You can't do this from one chemical to itself, but in a chemical series, water has more intermolecular forces than ammonia. And so ammonia is more likely to be a gas than water, just because the relative strength of the intermolecular forces. We use the word volatile a little bit differently than most language or English language. Volatile in regular speech is, kind of unstable. Volatility or non-volatility in chemistry is how much vapor pressure does something have? How readily does something evaporate from the liquid phase? Not once it's boiling, but when it's not boiling, how readily does that liquid turn into a gas. And so we can think of evaporation as some of these particles get enough energy that they can escape the intermolecular forces into the gas phase. Maybe they lose that energy eventually and they'll return to the liquid phase, but at this moment in time, they have enough energy to break away and they become a gas, or they vaporize themselves. Some portion of all liquids will be able to escape into the gas phase. This is true for solids too, but the percentage is much, much, much lower. So we typically only look at this in a reasonable way from liquids to gases. We will talk about sublimation for a second, where something goes from a solid to a gas instantaneously, but kind of more of a rare occurrence. But the higher the temperature, the larger the fraction is over this energy required to escape the liquid phase into the gas phase. Once all of the energy has been transferred to this, barrier, then you have exclusively the gas and no liquid. So evaporation and condensation are just reverses of each other. One's an exothermic process, one's an endothermic process. If I evaporate something, I'm taking something from the liquid phase and moving it into the gaseous phase. If I'm condensing something, I'm taking something from the gaseous phase and bringing it into the liquid phase. Gas phases are higher in energy than liquid phases. So if I'm going from the liquid to the gas, I'm going to have to add some amount of energy. That's going to be endothermic. If I'm giving off energy, if I'm going from a higher energy state to a lower energy state, that energy has to be released somehow. That would be an exothermic transition. So we can look at vapor pressure. We have some amount of vapor pressure until we've reached an equilibrium. So we haven't talked about equilibrium yet. Equilibrium is just when the forward rate equals the reverse rate. Chemical equilibrium is when the forward reaction equals the reverse reaction. We'll talk about this more in chapter 15, I believe. Maybe it's 14. But, if we don't have this capped, it'll continue to evaporate until all of the particles are gone. But at a certain point after we cap this, all of the particles that can escape will escape. And then the rate at which more particles escape is equal to the rate at which these particles in the gas phase lose their energy and go back into the liquid phase, which is what we define as the vapor pressure. So we can increase the vapor pressure by increasing the temperature. By increasing the temperature, we'll increase the relative amount of particles in the gas phase at equilibrium. If we decrease the strength of the forces holding everything together, more things will be able to escape into the gas phase, giving us a higher vapor pressure. Boiling is what we have when the vapor pressure equals atmospheric pressure or greater. It's not really common or useful to think about creating vapor pressure that's greater than the atmospheric pressure because it's only a temporary thing, and then, given expansion or some amount of time, the vapor pressure will eventually equal the actual pressure, or all of the liquid will turn into a gas. So thinking about vapor pressure being greater than the atmospheric pressure is kind of a trivial thing that we don't really do much. But boiling is defined once the vapor pressure hits the atmospheric pressure. So for water at 1 atmosphere, this happens to be 100 degrees Celsius. If we increase the atmospheric pressure, we're going to push these things together more. And so we're going to increase the total intermolecular forces, causing it to have a higher boiling point. If we reduce the pressure, we decrease the boiling point or reduce the amount of energy needed to separate molecules from each other. All that we're doing when we go into the gas phase is separating molecules from the intermolecular forces that bind them to the liquid and solid states. We can talk about heating curves, which is very useful because there's something that's a little, not intuitive about, changes of state. And that's called the change of state enthalpy. So depending on what change of state we're doing, we'll have different names. If we're going from a liquid to a gas, we call this the heat of vaporization. If we're going from a gas to a liquid, we call this the heat of condensation. Or typically we just call it the heat of vaporization and give it the opposite sign. For melting and freezing, we have the heat of fusion. So fusion is taking liquids to solids, so to speak. And so what happens is we can add temperature or remove temperature if we come from the other end till we get to the boiling point, the freezing point, the melting point, whatever physical state point we're talking about. In this case, we're talking about the boiling point. We can keep adding temperature, keep adding energy until we get to the boiling point. At some temperature that is the boiling point, we can continue to add energy, continue to add heat, but we won't change the temperature of the liquid. The reason for this is that energy is going directly, or the heat is going directly into separating these molecules from their intermolecular forces so they can transfer from the liquid to the gas. This is why you can have 100-degree water that is not boiling, and you can have 100-degree steam or gas that is not condensing into the liquid. As long as they're maintained at that temperature and they can't, release or gain the energy required to form the lower energy or higher energy phase, they won't transition states. And so this is a little unintuitive, but this is what happens for any phase change, is that some amount of energy is given to convert from one phase to another phase. Whether that energy is given to the particles or to the atmosphere depends on whether we're going from a higher energy or to a lower energy state. In the case of boiling, we're adding energy. So we're taking energy and adding it to the molecule so that they can overcome their intermolecular forces. We mentioned this. Evaporation is endothermic because it's going to take in energy. This is great for all sorts of processes. It's not super important to chemistry. It's just a way of referencing things. Condensation is the reverse. So if, evaporation is endothermic, takes in energy, condensation is going to get rid of energy. And so this is one thing why it explains why, getting burned by steam is worse than getting burned by water if you get burned by a similar amount. So fun things to know, but not great of importance to chemistry itself. Heat of vaporization is the enthalpy, kilojoules per mole, that we need to cause, 1 mole of thing to vaporize into the gas state from the liquid state. This number is going to be different for all sorts of elements. We can just relatively know that it's going to increase or decrease based off the intermolecular forces. So gasoline has less intermolecular forces than water, so we can assume that the heat of vaporization of water is going to be higher. So we mentioned this before, but endothermic and exothermic reactions have different delta H's. I forget which chapter we introduced this into, but it is a previous chapter we went over. If we have a positive enthalpy, that means we're taking in energy. If we're taking in energy, that's endothermic. Condensation is the opposite. We're giving off energy. If we're giving off energy, that's exothermic. We're reducing the energy of the system. That system has to go somewhere. It's leaving the chemical. So we can look at a whole variety of molecules with, lesser and lesser intermolecular forces. Acetone has less intermolecular forces than isopropanol, than water, and we can see that reflected in their boiling points and heat of vaporizations. Now, this is kind of a weird occurrence that it flips back and forth right here. This might actually just be a text error. I'm not entirely sure, but that's an anomaly that you usually don't see. So we can calculate these heats. If we have X number of moles, we multiply by the standard, enthalpy. We get the total enthalpy. We can be given the total enthalpy and the standard enthalpy and calculate moles. We can give the total enthalpy and the moles and calculate the standard. They're fairly simple. We'll do maybe 1 or 2 questions like this on exams and quizzes throughout the entire year. So not a big focus point, but you should be familiar that these type of calculations exist and that they're fairly simple to do. So if we have 150 kilojoules, we want to figure out how many grams of water. Well, they don't give us the heat of vaporization here, but it was given in a couple slides before. So we could take that 40.7 kilojoules per mole. We're starting with kilojoules, so we're going to reciprocate this ratio so that we have 1 mole of water per 40 kilojoules. Kilojoules will cancel out. We'll get moles of water. Then we can use the molar mass to calculate how many grams of water. Kind of back to chapters 6 and 8. So here would be the dimensional analysis. We'd get 68.6 grams at the end of the day if we were accounting for sig figs. We're not going to be doing that, so you could round to 69 if you chose. So make sure that everything makes sense. We can use our intuition. We had more than a mole of material. We should have, more than the standard enthalpy of energy, or vice versa. We should have more than a mole of mass. All these type of parallel consensuses can be made. So another example, in this case, we're given the mass in kilograms, so we have to convert kilograms to grams first, because our standard enthalpy is in kilojoules per mole. Moles is in terms of grams, so we need to make that conversion first. Then we can plug in our molar mass, and then the heat of vaporization that was given to us to get the total amount of energy. Whereas we were given the total amount of energy the first time, now we're doing the reverse process with kilograms. So melting and freezing are just the same as evaporation and condensation, except for their lower energy. So escaping to the gas phase is very high energy. We're going to have a high heat of vaporization. Melting is a little bit lower, so we're going to have a lower heat of fusion than heat of vaporization. So we can do the same thing that we did for steam and water as we can for ice and water. You can have 0 degree ice. You can have 0 degree water if we're talking in Celsius. The difference in terms of the internal energy there is the heat of fusion. So in here, we can see another heating curve where we add energy, and then at some point we can keep adding energy or keep adding heat, but there's no temperature change to the material until all of the material has done this phase transition. Once all of the material has broken its crystal lattice and is now in the free-formed liquid, then energy can be transferred to the internal energy rather than just the state of matter. Identical to, liquids and gases as solids and liquids are, just lower energies. So, kind of an explanation of endothermic versus exothermic with, melting and freezing instead of evaporation and condensation. Again, when we go to the higher energy phase from solid to liquid, we're going to take in energy. That's endothermic. We're going from the higher energy to the lower energy. We have to give off energy. That's going to be exothermic. So you can take a look at these, pause if you need. Heat of fusion is just our corollary to heat of vaporization. So heat of fusion, we mentioned that these are lower energy states, and so the energy of this transition is going to be much lower. 40 kilojoules versus 6 kilojoules. So just like our heat of vaporization, our heat of fusions will have positive enthalpies for the endothermic process, negative enthalpies for the exothermic process. Again, if we're going from a higher order phase of matter to higher order energy of matter to a lower energy of matter, we're going to have to give off energy. If we're going from a lower energy form of matter to a higher energy form of matter, we're going to have to increase the energy. So we can do these problems just like we did with the heat of vaporization. It's just our numbers will be slightly lower because the energy required to go from solid to liquid is lower than the energy required to go from liquid to gas, relatively. Every molecule is slightly different. So the difference from solid to liquid to gaseous water is different than solid to liquid to gaseous octane, gasoline, sugar, whatever chemical you want to insert there. We can only compare apples to apples. We can never really compare apples to oranges with much success. So here's a couple examples. We notice that the more or the less and less polar they are, the lower and lower their melting points are. Again, the heat of fusion of diethyl ether, I'm not sure if this is a misprint, but it's definitely an anomaly within the trend. So, given the amount of kilojoules, we can figure out how many grams of water we were able to melt or freeze given a certain amount. We absorb heat, so we know that we're melting. So we can do our solution map and then plug in our dimensional analysis to get our final mass of water that we were able to, melt with this amount of energy. We could do, our logical check, make sure this makes sense. We have more than the standard enthalpy of energy, so we should have more than just a single mole. 720 grams is a lot more. We have a lot more energy than the standard enthalpy of fusion. So we could do this with mass and convert to kilojoules. We could also give you mass in standard enthalpy and give you mass in the final enthalpy or the final heat, and then ask you to figure out what the standard enthalpy of fusion or vaporization is. But for now, we're just going from one end, either grams or kilojoules, and calculating for the other. Fairly straightforward. These calculations are essentially find your moles, multiply by your standard enthalpy. If you don't have moles, take your standard enthalpy and your total enthalpy, multiply them together. You'll get the respective answer. Sublimation is something that we don't really talk about much because it's hard to quantify. It's going directly from a solid to a gas. And sometimes, now CO2, the example we have here, never transitions to the liquid phase because of its intermolecular forces. However, water and ice are things that can sublime while also melting. So it's a complex process with multiple things potentially happening at one time. So we don't do calculations with this, but you should just know that sublimation is simply moving from the solid state to the gaseous state. And so here's an example of dry ice. You can actually see these wisps of vapor coming off of the dry ice. And so gas molecules or CO2 molecules are getting enough energy to escape from the solid phase directly into the gas phase. They never transition to the liquid phase, and this is because of the very unique nature of carbon dioxide. So intermolecular forces is the most important thing that we're going to talk about in this chapter. It's also purely conceptual, so there is no, plugging and chugging problem solving. It's very, shades of gray, big broad strokes of, this tends to be weaker, this tends to be stronger. But one thing we can say is the stronger the intermolecular forces, the stronger their physical properties are going to be. The higher their melting points, the higher their boiling points will be with more intermolecular forces. We have the book generalizes 4 different types of intermolecular interactions. I would argue that there's really only 3 intermolecular interactions, and I would call ion-dipole forces just another variation of dipole-dipole. And essentially, all of these are just dipole interactions of varying degrees. We've talked about dipoles a couple times. We talked about dipoles in chapter 10 as, are these molecules polar or nonpolar? We can have polar molecules due to polar bonds. That's the only way you get a polar molecule. Or you can get a nonpolar molecule that has nonpolar bonds, so there's no difference in electronegativity between the constituents. Or you can get a nonpolar molecule due to symmetry that has polar bonds. CO2 is a great example of this. CO2 has polar bonds, but is perfectly nonpolar because the polar bonds point in equal and opposite directions. So, dispersion forces are temporary dipoles. So they come on and come off on the millisecond, nanosecond timescale. They're very, very short-lived. Anything that's very short-lived can't be very impactful or very strong. If you flick the lights on for a millisecond, that's not very useful in finding anything in a dark room. Likewise, these dispersion forces or weak forces, van der Waals, London forces, these are all synonymous terms until you get into the very nitty-gritty physics. We generally call these weak force interactions or dispersion forces. These come from temporary dipoles that come on and off very quickly. Then we have dipole-dipole forces, which is a permanent dipole. This dipole, when we just call it a dipole-dipole interaction, is usually a very weak dipole, something with a moderate polarity, maybe, somewhere between 0.5 and 1 in a difference in electronegativity. So something like, carbon and nitrogen. They are different in electronegativity, but they're right next to each other. They're very similar. We're not talking about things like oxygen and hydrogen. Oxygen and hydrogen would form what we call a hydrogen bond. So a hydrogen bond is a specific type of bond that is very, very important to, physics, nature, biology. There's so much hydrogen. There's so much water in the world. Water is one of the biggest contributor to hydrogen bonding. And remember, intermolecular forces are between 2 molecules, not within the same molecule. So hydrogen bonding occurs between 2 molecules of water, whereas a dipole-dipole interaction might interact between two molecules of ammonia, or trimethyl ammonia, something like that. Doesn't really matter. Hydrogen bonding occurs when hydrogen is bound to nitrogen, oxygen, fluorine, or chlorine. That top right corner of the periodic table. These are dipole-dipole interactions that are just stronger than what we call a dipole-dipole force. They're all dipole-dipole interactions. This is just a temporary dipole. This is a dipole between things with moderate differences in electronegativity. This is a dipole between things with extreme differences in electronegativity. Oxygen and hydrogen have over a, 1 delta En. So ion dipole forces are kind of dipole-dipole forces, except for we have a full isolated charge in the shape of an ion. Instead of just partial positive and partial negative, we have a full positive or negative interacting with a partial positive or negative, depending on which pair we need to pair up with the full charge. So, dispersion forces, we kind of went over all this. They're coming from the syncing up of the electron cloud. So, the electrons can pair up. So, they can either be evenly distributed, randomly around the nuclei. Maybe they're a little bit closer to the nuclei, maybe they're a little bit further, but they're relatively distributed. However, by just statistical occurrence, just chance of luck, these two electrons can be moving in their own behaviors such a way that they come to the same side of the electron cloud. Once they come to the same side of the electron cloud gets this relative distribution of delta minus, where there's a slight aggregation of electrons, and a delta plus, where there's a slight deficit of electrons or lack of electrons. This isn't very impactful for small atoms, but as we add more and more and more electrons and bigger and bigger and bigger nuclei, or more and more atoms, this becomes more profound. So for a small molecule like H2O, it only has 3 atoms. It only has 3 electron clouds. They're all very light elements, very small nuclei. There's not a lot of this polarization that can happen. However, if you have something like ions or iodine that has a very, very large electron cloud, this electron cloud can be polarized or fluctuate very readily and causes a much more impactful temporary dipole. So as molecules get bigger and as electron clouds get more polarizable, weak forces increase. As we increase the total number of atoms, so too do weak forces increase. So we can create this type of dipole-dipole interaction, except for it's just temporary. These electrons are moving near the speed of light, and so only for some fraction of a second do they actually construct this type of arrangement where there's a delta minus to a delta plus to a delta minus to a delta plus, so on and so forth. This happens for nanoseconds, picoseconds, just fractions of seconds, just long enough that we can actually see that it's occurring, but not long enough to stay there and be a stronger force. So we mentioned all of these: increase the size of the electron cloud, increase the polarizability. So basically the difference in the delta positive and the delta negative. The more electrons that we can get to sync up together, the more impactful this is going to be. And then as we increase the amount of these things occurring, if you continually add 1 plus 1 plus 1 plus 1, if you add that 1,000,000 times, well, you get 1,000,000. But if you only add 1 plus 1 twice, it's a very small number. So we need a lot of these interactions to have any meaningful impact. Here's a couple examples of elements that just have van der Waals forces or weak forces. So the noble gases can only interact with things through their full electron cloud that precesses around and creates those temporary dipoles. Helium's boiling point is almost at absolute zero. Helium has never been observed to be a solid, and theoretically it never will. Neon, incredibly low. As we get to these bigger and bigger nuclei, 165 Kelvin is pretty low. That's probably a lower temperature than any of you guys have ever experienced. I've worked with liquid nitrogen, things like that. If you've been in a lab, you've seen things colder than this, but this is a very cold temperature. We don't get these temperatures on Earth. And so xenon is pretty much a gas, no matter what, or a liquid or a gas, no matter what. Argon, is a liquid at minus 50 degrees Celsius. So that's pretty close to its Kelvin temperature. So minus 50 Celsius or minus 60 Celsius is around this degree Kelvin. So moving to the next forces, dipole-dipole forces. These are permanent dipoles. Previously, we had temporary dipoles. Now we have permanent dipoles. These dipoles don't fluctuate. They don't come on and come off. They're permanent. They're always there. And so we can look at polar molecules to have dipole-dipole interactions. If you don't have a polar molecule, a non-polar molecule cannot interact with dipole-dipole interactions, even if it has a polar bond. CO2 does not have any dipole-dipole interactions, and that's why it maintains its behavior as a gas for so long. So formaldehyde is a great example where we have this, partially positive carbon that's attached to this partially negative oxygen. Oxygen is just more electronegative. It's just going to tend to pull more of the electrons its way. It's going to always have a statistical excess of electrons compared to carbon. Carbon will always have a statistical deficit of electrons. And so no matter what, no matter how the electrons are moving, precessing, whatever, you will always have some amount of positive charge on carbon and some amount of negative charge on oxygen. And so these things can pair up in this dipole-dipole type of interaction. Formaldehyde has a dipole. Ethane is a similar molecule that does not have a dipole. And we can see the very big difference in their physical transitions. It takes a lot more energy to transition formaldehyde from state to state because it's bonded together through its intermolecular forces through these dipole-dipole interactions, where ethane only has the weak force interactions. It's only using its electron clouds to temporarily create dipoles. Formaldehyde has a permanent dipole. So we've talked about solubility, but miscibility is kind of this, characteristic that we give to liquids. So if you have a solid or a gas that's soluble in a liquid, we say that it dissolves. If we have a liquid that dissolves into another liquid, we say they're miscible. If they don't mix, like oil and water, we call this immiscible. Alcohol and water are fully miscible. You can mix them together at any ratio. So over here, we have essentially gasoline and water, pentane. That's a slightly smaller molecule than octane, but still the same thing. It's very nonpolar, carbon-hydrogen bonds. Water has oxygen-hydrogen bonds. Very big difference. One will sit on top of the other will sink to the bottom. That's just determined on density. Organic molecules tend to have a lighter density than water or non-organic molecules. Here we have, some type of oil over vinegar, which vinegar is mostly water. And then an oil spill. We've all seen pictures or even in real life where oil sits on top of water and it creates these kind of splotchy areas. And that's just because there's not enough volume of the oil to fully sit on top of the water. So you get these kind of ripple patterns. Now we need to talk about what the result of all the different dipole-dipole interactions are within a molecule. We talked about this with CO2, where we have two polar bonds, oxygen bonded to carbon, electronegativity difference of about 1. These are considered polar, right between, nonpolar and ionic. 0.4 is considered our cutoff for nonpolar. 2.0 is considered our cutoff for ionic. So this sits, right in the middle of there pretty much. But because this oxygen pulls this way and this oxygen pulls that way, they pull even and opposite. And so because of the symmetry of this molecule, these polar bonds become nonpolar overall throughout the entire molecule. If we look at something like dichloromethane, where we don't have a truly symmetric molecule, these arrows on the hydrogen should be pointing in. I don't know why the book does this, but they mention right here that carbon is more electronegative than hydrogen. So these arrows should be pointing in. And so the net dipole is going this direction. That's in opposition to something that's fully symmetric. So all of these hydrogens are pointing in. They're not pointing out like the book shows. Again, this is just poor publishing. They're pointing in. And so there's slightly more electron density on carbon than there is hydrogen, but not enough to call this a polar molecule. It's not perfectly nonpolar, like carbon bonded to carbon, or hydrogen bonded to hydrogen, or any element bonded to itself. But the lack of a large electronegativity difference, 0.4, is our cutoff for nonpolar. So there's barely any difference in electronegativity here. barely any separation of electrons between carbon and hydrogen. They're very equally shared. So hydrogen bonding, that is our, third classification of intermolecular forces. Every intermolecular force is just a larger and larger dipole. So the first one we talked about were those weak forces. Those are the temporary dipoles. Then we talked about dipole-dipole interactions. That's just a permanent dipole. Now we're talking about a dipole or a super dipole between very, very electronegative elements. The book says fluorine, nitrogen, and oxygen are the only things that undergo hydrogen bonding. Chlorine has almost the exact same electronegativity as nitrogen within so many decimal points that most textbooks will give them the exact same electronegativity. Chlorine bonded to hydrogen also has a hydrogen bond. The book is just wrong here, just like with those polarity arrows. Unfortunately, the book just has a couple issues when it comes to electronegativity and the things that fall out of that. So if we have hydrogen bonded to fluorine, oxygen, nitrogen, or chlorine, we're going to have hydrogen bonding. These are just much stronger dipole-dipole interactions. And so if we have a larger magnitude of force behind the interaction, we're going to have a larger interaction or a greater, stronger interaction. So, this is between molecules, not of the same molecules. So we don't talk about hydrogen bonding between oxygen and hydrogen of the same molecule. It's between oxygen and hydrogen, or fluorine and hydrogen, nitrogen, hydrogen, chlorine and hydrogen, and another molecule of a similar orientation. So in here we have multiple molecules of HF. There's no hydrogen bonding between hydrogen and fluoride within the molecule, intramolecularly. The intramolecular association is the covalent bond, or ionic bond, depends on how you want to think of this. Hydrogen fluoride is fairly ionic. It's a 1.9 on the electronegativity scale, or delta En scale. A lot of books will call that ionic. Our book calls it superpolar covalent. But we can have this, intramolecular interaction, and then we have the intermolecular interaction. Because there's an extreme difference in electronegativity between fluorine and hydrogen, we define this as hydrogen bonding, one step up above those permanent dipole-dipole interactions. So we could see this with methanol. This is a nonpolar residue. It's not really going to interact. You'll have the same delta minus and delta plus between oxygen and carbon, but there's a bigger electronegativity difference here. So this is hydrogen bonding, whereas oxygen and carbon would be a dipole-dipole interaction. Because this has a larger magnitude of charge separation, it has a stronger interaction. So methanol compared to ethane, we see an increase in the intermolecular forces, so much so there's almost 100 degrees difference between their melting and boiling points. Pretty substantial just from one hydrogen bond. Water has 2 hydrogen bonds, and so that's why the boiling point of water is significantly higher than methanol. So water has these 2 type of hydrogen bondings. Water is, 70% of our body. Similar proportions exist for most other life forms on Earth. And so hydrogen bonding with water molecules and proteins and other things in biology are very, very predominant and very important. It's kind of why we came up with this specific dipole-dipole interaction that we call hydrogen bonding. Next step up is we talked about, temporary dipoles, then we talked about permanent dipoles, then we talked about really strong dipoles. Now we have such a strong dipole that we have a full negative charge. We said if the magnitude of charge difference or the isolation of charge increases, so too does the intermolecular forces. Well, if I have partial positive interacting with partial negative between 2 water molecules, it's a very strong interaction. But if I have a full negative interacting with a partial positive, because this full negative is a larger force than just a partial negative, the interaction between these 2 things, or all of these things, is going to be much greater. Most people will just call this, ionic interactions, but the book specifically calls this ion dipole forces instead of like solubilizing forces or anything like this. This is basically the definition of solubility of an ionic compound. You have some, electrostatic or ion dipole interaction that separates the crystal lattice between chlorine and sodium. And so All the sodiums on the outside of this chlorine sphere would be the sodiums facing the heads of the water molecules, where the tails are kind of pointing at the anionic charge. The heads would point at the cationic charge. So here is our kind of examples. We have temporary dipoles where the electron clouds sync up. We then have these permanent dipoles where they're always delta plus and delta minus. This delta plus and delta minus come on and off very readily, and so that's very weak. We have hydrogen bonding, so if we really increase the strength of this dipole, we get a stronger interaction. If we increase the separation of charge so much that we get pure, positive or pure negative charge interacting with partial charges, because the magnitude is greater, the interaction is also going to be greater. The last thing that we're going to talk about, only because it's in the book, is solids. So we have 3 different types of solids. I have never seen this type of, dichotomy of solids before. Typically, we talk about things as molecular solids or atomic solids. Ionic solids are just kind of grouped in with molecular solids. This is a very weird ordering. We're just going to talk about it as the book does it. So this is their definitions. You can break them up into molecular solids. Molecular solids are anything that is composed of covalent compounds. We'll get into a little caveat here. Ionic compounds are things that actually, don't form covalent bonds, but they form ionic or electrostatic interactions, full positives, full negatives. These result in higher melting points or stronger intermolecular forces. Molecules can just have, the hydrogen bonding, dipole, and weak force. These have those, ion dipoles, so a little bit stronger. And then we have what they call atomic solids. Atomic solid is not a common definition. I have never heard the use of atomic solids. We usually call them metallic solids or elemental solids. Atomic solids is just a very awkward thing, and I'm going to point out why it's kind of flawed. I'm not going to ask you too much on this stuff, but it is in the book, so you should hear about it. Molecular solids, water, CO2, these are just our everyday things. They're held together by weak forces, dispersion forces, dipole, hydrogen bonding. Maybe if it's a polyatomic, you'll see some type of dipole ion, but then we're getting more into the regime of ionic solids. So big, wide ranges for molecular solids is ultimately what we figure out. Dry ice, minus 78 degrees C, whereas water is 0 C. So huge difference. And it's because this only has weak forces, and this has hydrogen bonding as well as weak forces. Ionic solids are just any ionic compound. Because the electrostatic attraction between them is so strong, to actually melt them or break that lattice requires a good amount of energy. Now, the energy of solvation is a lot stronger than you'd think. And so a couple drops of water compared to sodium chloride is enough energy or enough stability to actually dissolve the solid, break the crystal lattice, where it takes, 700 to 900 degrees Celsius. I'm not sure the exact melting point of, sodium chloride, but sodium chloride has an extremely high melting point in the absence of some polar solvent because those interactions are very stable. So here's just an example. Sodium chloride, 801 degrees Celsius. Carbon disulfide is a molecule, minus 110 Celsius. So more like dry ice, because, it has a very similar structure to dry ice. Instead of carbon dioxide, it's carbon disulfide. Sulfide is less electronegative, so it's going to have less intermolecular forces, and because of that, we have a lower melting point. Atomic solids is really where the book falls off. They call covalent atomic solids, which is essentially a made-up term. Covalent atomic solids anywhere else are called network solids, and they're included with covalent compounds. Diamond is a covalent compound. It is not an atomic composition. It's not just a whole bunch of carbon elements together. That's what the book would kind of lead you into believing. Diamond is a perfectly tetrahedral arrangement of pure carbon atoms. That's what it is. It is a covalent molecule. It's just such a large covalent molecule that it cannot exist in the liquid or gaseous form. And that's just because of its molecular weight. So its molar mass is in the tens of thousands of grams per mole. Whereas, Water has a molar mass of 18. As molar mass increases, so does its propensity to be a solid. So too do its weak force interactions increase. Non-bonding atomic solids, these are noble gases. None of the noble gases exist as solids, and so no one calls them solids. We call them the noble gases, not non-bonding atomic solids. This is a very silly definition. Metallic solids, which they call metallic atomic solids, are just called metallic solids because you can have pure metal, pure iron, pure copper, pure magnesium, and those would fall into this classification of metal atomic solids. What happens when you make alloys? Alloys are solid. Well, now you have a metal solid that's not atomic, and you have to come up with a whole new classification. The book tries to simplify this, and by simplifying it, they just make a whole bunch of mistakes that are just fundamentally wrong. I'm not going to ask you about the melting points and boiling points of solids because the book does such a bad treatment on it. But in general, our covalent solids have the highest melting points. Our noble gas solids are non-bonding solids, which is stupid, because xenon, the one they have here, actually does engage in bonding. So everything about this is just wrong. They have the lowest melting points. The noble gases only interact via weak forces, so of course they'd have the lowest melting and boiling points. Metals are a big group of things. We have metals like gold, silver, tungsten that are solid until you get to very high temperatures. And then you have very, soft metals like mercury, gallium, sodium. These are things that melt at relatively low temperatures. And so, not the greatest classification scheme that the book invented on their own behalf. So, covalent bonds are the strongest thing. You can't break covalent bonds by just adding water to them. If you add water to alcohol, you don't do a chemical change. You don't separate or ionize the chemical bonds. But if you throw sodium chloride into water, water quickly ionizes those elements. It quickly separates them into, Na+, Cl-. That's essentially the reason why covalent solids, or what you should know as network solids, diamond is a network solid of carbon, have much higher melting points than their covalent solids. They say a three-dimensional hexagonal pattern. That's kind of true. You do have these hexagons if you look at it, but truly, if you look at the individual atom, this is a tetrahedral center. The book tries to make things simple, but they just end up stepping on their toes. I don't know why they do this. Maybe they don't know better. I would hope they do. But this is just a tetrahedral arrangement of carbon atoms. Yes, if you create tetrahedrons over a large space, they do make these distorted hexagons. But why make something more complicated when you can distill it down to the functional unit rather than 1, 2, 3, 4, 5, 6 functional units? Just doesn't make sense. Non-bonding solids, they're noble gases. No one calls them non-bonding solids. Everyone calls them noble gases because unless you've dealt with the most extreme temperature regions in the universe, you're never going to see a noble gas as a solid. I've been a chemist for 10 years. I've worked with almost every single noble gas that's naturally occurring. Only one of them have I ever seen as a solid. So, metallic solids, these are everywhere. They have such a large variety, mercury minus 39 degrees Celsius to, iron, which is not even the highest melting metal. Tungsten is the highest melting metal. If you make tungsten carbide melts at a higher temperature than the surface of the sun. So metals have all sorts of variety properties. No point in memorizing them. So one thing we can talk about is that metallic solids, or metals in general, they tend to delocalize their electrons over the entire species. So rather than having electrons isolated to one species or shared between species, these electrons are shared between all species, not just 2 atoms, not just 3 atoms, but every single atom in the sample. And so that's why sometimes they call it a sea of electrons, or the book says electron sea. This is referred to as an electron band because all of these electrons, depending on how close to the edge of the material or how close to the center or how many defects in the material are present, they all have slightly different energies. So instead of saying for a specific molecule, we would say, the electron energy is 10 electron volts. Whereas in a metal, we would say the band gap energy, the average energy of all the electrons in this metal, is between 5 and 10 electron volts. We give it a range because each electron has a slightly different value, but all of the electrons are accessible to any given metal center. This is a little more complicated, and if you get into inorganic chemistry classes, we definitely go into this in more depth, but we just want to know that electrons are just delocalized across the entire metal. This is why they're so conductive. Nonmetals, they hold on to their electrons between elements, and so they don't conduct electricity. They don't conduct temperature very well. Metals, they have this free flow of electrons between any given atom anywhere in the material, and so electricity, which is just electrons, flows through the material very well. Heat, transfers as a very similar property, but it's a little bit more complex theoretically. So we covered a whole bunch of different things. The main focus is our intermolecular forces. You need to be able to rank the intermolecular forces from the temporary dipoles to the permanent dipoles to the very strong dipoles to the extremely strong dipoles. The intermolecular forces are what determine all the physical properties of a compound. We can talk about crystalline solids, but the book does such an awful job at this, making up their own definitions and designations, that we're not going to really talk about this. So, again, key concepts, intermolecular forces, you need to be able to rationalize them. What do they mean? If I have more intermolecular forces, my boiling point, my melting point is going to increase, my vapor pressures will decrease. Energy and heat, we could do a couple calculations for the endothermic and exothermic transitions of state. Obviously heating is involved in that, but melting and freezing, evaporation and condensation, those are endothermic and exothermic processes. They're just reverses of each other. We can do a couple calculations. If I have 5 moles of some compound, I know the heat of fusion. I can figure out how much energy it takes to melt that sample. Pretty much all we'll do with those heat and energy calculations. The correlation of intermolecular forces to physical properties is much more important. If I give you a series of chemicals with more and more intermolecular forces, one, you should be able to determine which one has the most intermolecular forces, as well as what those intermolecular forces mean in terms of the boiling point or the melting point or other physical properties. So if you have any questions on any of this stuff, please make sure to reach out. Otherwise, I'll see you next week. We do have the exam covering chapters 9 through 12 next week. So if you have any questions, you need extra copies of the challenge question, make sure to reach out. Otherwise, I'll see you then.